All right, good morning, everyone. So today we're going to talk about two kinds of structure from motion. The first one is incremental perspective structure from motion, where you're growing a solution over time and solving for perspective images. And the second is a global affine structure from motion, where you solve for the pose and points all at once, and it's for an affine camera model or orthographic camera model. So originally I was actually going to try to make your homework problem based on incremental perspective structure from motion, and then I realized that it was extremely painful for me, and it would probably be at least as painful for you. And so I decided to stick with affine structure from motion as your homework problem. But I still want to, they're both kind of interesting in different ways. So in practice, incremental perspective is used a lot more often. So that's like what you would typically have if you have like an internet image set, or you're taking a video or something and you're trying to reconstruct 3D scenes, then you'd be using that. The reason why it's not easy to do as a homework problem is that there's like the simple way to do things, and then there's the way that works, and they're different. So solving for things as linear systems of equations tends not to give good results. So I didn't want to make you do bundle adjustment and minimize reprojection error and stuff like that. So just to remind you of two of the major concepts from the last class that we're going to reuse. One is epipolar geometry. So the basic idea of estimating 3D points from images is that you need to solve the pose of those images, and then you can triangulate to solve for the 3D points. And so epipolar geometry gives us one of the main constraints between two camera poses that are of different positions. And that is that if you have a point in the scene imaged onto one of the cameras, then the essential matrix will relate these two cameras. And the essential matrix will map from a point in one image onto the epipolar line in the other image, or from a point in the second image onto the epipolar line in the first image. And the epipolar lines will all pass through the epipoles of a camera. And the epipole is the projection of one camera's center onto the other camera's image plane. So if you're trying to match a point, then given some point on the point X where it appears in the first image, you know that it lies somewhere on this ray from the camera center through this pixel. So somewhere along this ray, and that will correspond to a line, and that line is given to you by the essential matrix or the fundamental matrix. So if you know the intrinsics, then you can get the essential matrix, which has 5 parameters. If not, then you can solve for the fundamental matrix, which has 7 free parameters. Either one maps from a point in one image to a line in the other image. But from the essential matrix, you can actually recover the relative rotation and translation between two cameras as well. So this is all like how you relate two cameras to each other. And the major difference of structure from motion in general is that you have a whole set of cameras. So now you don't want to just relate camera 1 to camera 2, but you want to relate all of the cameras to each other, so estimate their pose in some kind of coordinate system, and then estimate the positions of the scene points in that same coordinate system. So for example, here you've got like a whole set of internet photos, and then the structure from motion algorithm solves for the pose of all these cameras, and solves for the 3D points of the Colosseum. So this is the broad outline for incremental structure from motion. You first compute features, so typically SIFT or something like that. Then you match images to each other by matching features and solving for a transformation between the images and finding inliers. And then you do reconstruction, where you iteratively, first you initialize by solving for pose and 3D points from two cameras, and then you iteratively solve for the pose of another camera that has points in common with the first ones, and then solve for new 3D points that are seen by at least two cameras with reconstructed poses, and do bundle adjustment to try to minimize the reprojection error, and then keep on repeating that. But I'm going to go through these in some detail, and the details are actually important to have a successful algorithm. So a lot of this basic framework is in common among almost, well, pretty much all incremental structure from motion approaches. But I'm particularly drawing from OpenSFM, so I'm going through kind of the general algorithm for OpenSFM. So first you detect features, and it's very common for people to use SIFT. There's also brief features, which are used by OrbSlam. You can use Hessian Laplace features or histogram of gradient features. But they're always usually some kind of SIFT-like feature that allows you to get robust matching across changes in viewpoint and is robust to changes in lighting. And so here in this representation, we've got a set of n images, and we've detected features in these images. And so you can think of these circles as like a set of features that has been detected. So typically, you'll detect somewhere between 1 and 4,000 features per image, and that ends the feature detection phase. So then you want to try to match features and images. So you just have, at this point, you've got a whole set of images, features for every image. You have no idea how the images are related to each other. So the first step is to figure out, to find some correspondences between the images. So for every pair of images, you compute the feature descriptors and then match them using typically approximate nearest neighbor. So you could use like locality-sensitive hashing or cascaded hashing, some kind of approximate, some kind of hash function so that you can match features very quickly. Because if you have 1,000 features, that means that you need to match between 500,000 pairs of images. So, and you've got a few thousand features per image, so you need to do a lot of matches. So usually, instead of doing a brute force match where you can compute the Euclidean distance between pairs of features, you'll do find approximate nearest neighbors or use KD trees or some other more efficient structure. Then, then given candidate matches, then you can use ransack and solve for the fundamental matrix that relates the two cameras to each other, and then keep the inliers. So then at the end of this process, for many pairs of images, you'll say that you don't think there's a match between them at all because you can't solve for a fundamental matrix that has a lot of inliers. And for other ones, you might say these two images match, and these are the like 800 points that are consistent with some fundamental matrix. So these are my current inliers. There's a lot of tricks to try to improve this process. So brute force matching takes like a couple seconds per match for every pair of images. So if you've got to do 500,000 matches, then that's going to take a really long time. That's 1,000,000 seconds. So, so approximate nearest neighbor is one thing that makes it significantly faster. But then there's a lot of other tricks. So one thing that was proposed by Wu in Visual SFM is that you only match the largest SIFT points first. So by largest, I mean that they have like the highest scale. And he found that usually if images match, then the large key points will match more reliably because they're less sensitive to noise since they're lower resolution. And so if you just match the top 100, the largest 100 features in each pair of images, and then require that you have at least like 4 matches between them, then you can quickly go through, you can quickly find candidates. It only takes about 50 milliseconds to do that versus 2 seconds for full matching. It's also really common to use bag of words methods, which we'll talk about more in the next class, to try to find candidate sets of matches. So that's where you cluster your key points and then compare histograms or do inverse indexing to try to find similar images. That we'll discuss in next class. And then another common thing is if you have GPS coordinates, like if you took your pictures by drone or by a camera that, if you're taking snapshots with a camera that has GPS, like a phone, then you can enforce a constraint that you're only going to match to the nearest K images based on the GPS coordinates. So then that makes your problem a lot less computationally heavy. And then the final one, which is more complicated, is that you can try to use known matches to predict new ones. So as a simple example, if A matches B and B matches C, then you also want to check to see if A and C match. And there's ways of building up all of the matches to try to use the matches that you've already found to find new likely matches without having to do exhaustive matching. So now let's say that we've matched the features. And so now here, like the red circle means that these two images see like this set of features represented by the red circle. The first 3 images all see this set of features represented by the blue circle, and so on. And so we've got correspondences now between the images. So the next step is to create what's called a tracks graph, or maybe there's other words for it, but basically we change the representation from thinking about it as we've got features that have pairwise matches between images to that we have tracks which correspond to observations of 3D points, and some set of images match each of those tracks. So now, like for these green points, I'm trying to use the cursor so it works on the video later. So like this green point this corresponds to some 3D point or set of points that is seen by both of these images. And so I've got 2D observations of this 3D point in this image and 2D observations in this image. Because they match, I'll assume that they correspond to the same 3D point. And so in this graph, I've got a node to represent that 3D point. And then there's an edge from that to each of the first 2 images to show that image 1 sees this green point, image 2 sees that green point, image 1, 2, and 3 see, image 1 and 2 see the red point, image 1, 2, and 3 see the blue point, and so on. And so now the goal of structure from motion is to then solve for all the positions, or as many as possible, of these 3D points and the poses of all the images. And so mainly this tracks graph, which is a bipartite graph between observed 3D points and images, just makes it a lot easier to, it's a data structure that makes it simpler to think about the problem. And it's common to even apply graph-based algorithms to improve structure from motion, looking to see, for example, like clustering your images based on spectral clustering algorithms. So then we need to start somewhere. So we want to reconstruct everything, but so far we have nothing. So you start by selecting a pair of images. And usually you want to choose a pair where they have a lot of inliers, so a lot of matched features that agree with the fundamental matrix. But remember that the fundamental matrix is degenerate if all of your points are on a plane. So if all of my points between 2 images were on a plane like this wall, then I could account for those points either using the fundamental matrix or using a homography, because homography is a plane-to-plane matching. So if I've got two images that are observing all points on a plane, then I can find a homography to relate those points to each other. So usually you check to see that you've got a lot of, that most of your, or at least many of your matched points cannot be accounted for by a homography, to make sure that you're not just imaging a plane from two images. So you check to see what is the number of inliers for estimate of the homography between the images, and what's the number of inliers for the fundamental matrix, and check that it's less than 0.7. And also, otherwise, you want to have a lot of inliers. So that's how you choose your first pair. Then you typically get the focal lengths from EXIF data, which is usually available. If not, you just make some guess at the focal length based on a typical value, and estimate the essential matrix using David Nister's 5-point algorithm, which is a nonlinear algorithm for estimating the essential matrix. Since it has 5 free parameters, 5 points is and every pair of points gives you one constraint. 5 points is the minimal number of 5 correspondences is the minimal number of correspondences you need. So you use like a Van Sack with the 5-point algorithm to estimate the essential matrix. Then from the essential matrix, you can extract the rotation and translation of the second camera compared to the first camera. So you'll say that the first camera has identity rotation and a translation of 0. And then the second camera has some RNT, which is just extracted from the essential matrix by some fairly straightforward linear algebra. So now we've got the pose of image 1 relative to 2. So I've put them in red because those are the images that are in play right now. And then we want to solve for some of the 3D points. So now we can solve for any point that's observed by both 1 and 2, we can estimate its 3D position. And I'll get to that in the next slides in some detail. And then we can perform bundle adjustment to try to refine the points and poses for these two cameras by themselves. So so now I'm just going to, once you create this tracks graph, you no longer have to worry about features or correspondences or anything. You're just working straight from a tracks graph, from this graph. This graph is your entire representation of the structure for motion problem. And so here I'm representing filled circles are points that have been reconstructed, and filled images are images that have been reconstructed. Or in the structure for motion parlance, points have been triangulated, meaning I know their values, and images have been resectioned. I don't know where that comes from, but it means that I've solved for the pose. Okay, so the one thing that I haven't talked about in that slide in the previous class is how do you solve for the 3D points given a set of corresponding images. We talked about using stereo algorithms, but the algorithms that we talked about only apply for 2 images. And so here we're going to want a more general solution that applies if you have multiple images observing the same point. So first the linear solution, which establishes the concept. So the basic idea is that you have, for every image that you observe a 2D point of this unknown 3D point, you have a constraint that says that the projection of x, or px, where p is the projection matrix of this image, p times big X should be approximately equal to little x, right? And then in this image, p prime times x should be approximately equal to x prime. So given the projection matrices of each of your cameras, you've got a pair of constraints that say that the 3D point should project close to the 2D coordinate where you observe it. So then we can set this up as a system of homogeneous linear equations. You can just, P would be known values in this case. You get P is K times RT. So at this point, we're assuming that we've solved for rotation, translation, and intrinsics. And so we just get, for every point, we get a pair of equations, one for the U value and one for the V value. And then I've got it in my typical system of homogeneous linear equations, which I can solve using SVD. So similar to how we did this for many other problems. So this, the nice thing about this is that you can have any number you can solve for any number of corresponding images. So as you get more images, you'll get more over-constrained, but you should have a better estimate, assuming that your images are observing the 3D point with some noise and you don't have any outliers. The downside of this is that it's not projectively invariant. So the same problem that we had trying to estimate the fundamental matrix, that we're solving for these matches, and we're solving for this projection in homogeneous coordinates, and it doesn't correspond to the reprojection error, which is really what we want to optimize. So in practice, you might initialize by triangulation, but you really want to minimize the projected error while satisfying the epipolar constraint between the pair of images, if you're solving for two images, or otherwise just minimize the reprojection error. So you want to, so if you're triangulating based on two images, then you can say, I want my 3D point X to project as closely as possible to this point here, where by closely as possible I mean the Euclidean distance between the projected point and the observed point, and the same in the other image. And then the distance between those, and I can constrain that my projection will lie on the fundamental matrix. I mean, on the epipolar line that comes from the fundamental or essential matrix. So if I assume that these points are detected with some amount of noise, but that my essential matrix or fundamental matrix is probably estimated with less noise because it can be estimated based on many points, then I can constrain my triangulated solution to project back to the epipolar lines, since I may trust my epipolar lines more than I trust the individually detected points. So I want to try to minimize this distance, but also constrain the projected points to lie on the corresponding epipolar lines. And it turns out that this is that the solution is minimizing a 6-degree polynomial in terms of a single variable t. But it's complicated, but if you ever wanted to do it, then you would spend a couple hours understanding it, implement it, and then forget it the next day. So that's triangulation. Bundle adjustment is when you want to try to solve for both the camera poses and the 3D points at the same time to minimize the reprojection error. So basically with incremental structure for motion, you solve for pose, then you solve for 3D points, and then you solve for them both jointly. And so it's pretty easy to write down your optimization function. You're trying to minimize the square distance between the projected points. So for camera I, you have some projection matrix Pi, which is Ki times Ri Ti. And then 3D point J, so you've got some set of cameras. Here it's just assuming that every camera sees every point, but in practice you might have only a subset of cameras that see each point. And you want to minimize the square distance between the projection of the 3D point and the observed point. And that will be done using some form of gradient descent or some kind of nonlinear optimization. And there's been a lot of work on being able to solve this efficiently. So a lot of the work that's in structure from motion is being able to skip computation by like not even testing matches if you think that it's not going to pan out, and being able to efficiently do large optimization problems. So also one thing to note is that here it's written as a squared error, but it's common to use a Huber loss, which is that you have a squared error within some small range, but then it just becomes linear. And the reason for that is that you don't want, if you have an outlier, you don't want a large error in that outlier to like twist your whole solution, which if you have a squared loss, it gets really large really quickly. So your outliers will dominate the solution. So Huber loss, for example, would be a squared error within a distance of 1, and then linear after that, with a slope of 1. So, so now we've got, so far we've solved for the pose of 2 cameras and the 3D values of the points that they observe, that they both observe. And so now I can grow my reconstruction. So I iteratively resection, which means that I add other cameras to my solution. So I'd solve for, typically you would add cameras in order of how many triangulated points they see. So in this case, image number 3 sees some points from that have been already solved for by image number 1 and 2, so this set of points here. And so now based on these points, I can solve for the pose of image 3. So that's what I mean. I'm representing this as like a set of points. So I solve for the pose of image 3, and then once I've solved for the poses of image 3, now I've got some points that are observed by image 2 and 3, so I can solve for the 3D values of those points. So that's the triangulation. So I do resectioning and then triangulation. Then you need to remove points that are outliers. So you need to check to see if any observations are inconsistent with your 3D points. And either get rid of those observations or just throw out the 3D points entirely, because outliers can quickly ruin your solution if you don't check them. It's also common to check to see, you want to make sure that that if you draw a line from one camera center into the 3D point and then back to a second camera center, you don't want that angle to be too small, because it means if the angle is really small, then your estimate of the distance of the point will be really unstable. So you can imagine, like, if you had 2 cameras that are right in front of each other, and you're observing a point straight through the center of both images, that point could really be anywhere along that line. And then if you perturb a little bit, you'll get an estimate for the 3D position of that point, but it will be really unstable. So you might end up thinking that you see a point that's like 5 miles away. And that kind of thing can destroy your whole solution. So you need to be pretty careful with checking for outliers. Then you do bundle adjustment. So another kind of speed tip is that usually in like the simplest version, you add one image at a time and then do bundle adjustment for your whole solution. That ends up being O of n cubed, which of course gets really big quickly. So it's common to only do to either skip bundle adjustment until you add some % of new images, or only do a local bundle adjustment. So you can just try to like refine the last few images that you added until you add like 5% of new images. So if you currently have 100 images in your solution, you add 5 new images, and then you do bundle adjustment. And then you add 5 more, and then you do bundle adjustment. And then when you get to 1,000 images, you're going to be adding 50 images before you do bundle adjustment. So that actually changes the run complexity. It makes a huge difference if you're doing large reconstructions. Then sometimes you want to try to align your points to some world frame. So remember that all of this all of structure from motion can only solve for points and cameras up to some kind of similarity transform, even if you have the intrinsics. So if you want to try to align your 3D points to the world, then you need to either have some ground control points, which are points that are observed by the cameras where you know their 3D position in the world, or you need GPS data or some kind of absolute camera pose for some of your cameras. So you can then, like during the structure from motion process, compute a similarity transform between your camera poses and whatever known points you have. So then you just keep on iterating through this. So now you keep on adding new cameras, then solving for points that are now seen by at least 2 cameras, doing bundle adjustment, getting rid of outliers, and then you iterate through that until you're done. So that's the whole incremental structure from motion process. So I just want to highlight some recent and important papers on this topic, if this is something that you're interested in and you want to look into it in more detail. So first, a couple of tools. So there's actually, within the last few years, there's actually been 4 or 5 different open source platforms for structure from motion that have been introduced. But the 2 that I've worked with the most that I think are good are OpenMVG, which includes structure from motion and dense multi-view stereo and surface reconstruction, and OpenSFM, which also actually includes all those things. So OpenMVG is in C++. OpenSFM is in a mix of Python and C++. OpenSFM is very recent. It was released last fall. And it's and what I like about it is that it's a lot easier to work with because you can do all the high-level stuff is in Python, and but it's actually faster than OpenMVG, and actually it's as fast or faster with some fairly simple modifications than any of the other platforms that I've used. And it's just nicely written code. So I like OpenSFM. There's this paper by Pierre Moulin, who created OpenMVG, is a really good paper to read because it covers a lot of the recent techniques and as well as their own contributions in that paper. And then this Visual SFM paper is also a good paper to read. Visual SFM for a while was the best structure from motion system out there. It's closed source though, and it's not the best algorithm out there anymore. But a lot of the tricks that Wu introduced are used by other systems. And it's basically like Visual SFM, the main contribution was taking SFM from a quadratic or cubic runtime to a linear runtime. So he introduced some tricks for matching, the idea of like finding the matches between large key points first, and for bundle adjustment and doing local bundle adjustments most of the time, and only doing global on some kind of ratio scale that made SFM a lot faster. So there's a video here if you want to see it later, but I'm going to show you some other examples instead. All right, so that's structure from motion. So now at this point, I've got for my set of images, I've solved for the poses of the cameras for as many as possible. And I also have a sparse set of points, 3D points. I have 3D points that were detected by the SIFT detector and where I found correspondences among cameras whose poses I reconstructed. So often we want to go a bit further. We want to create some kind of dense 3D point cloud or a surface. So I'm just going to mainly have pointers to these algorithms and describe them at a very high level because they're also pretty complicated by themselves. So, so the problem of taking a whole set of localized images and then computing a dense point cloud or computing a depth map for every image is called multi-view stereo. multi-view because there's more than one camera, stereo, getting depth. So the main difference between multi-view stereo and like normal 2-image stereo is that besides that you have more images, that you usually solve for it in terms of patches. So instead of just reconstructing individual points, you'll solve for the depth and surface normal and relative lighting of little like 3x3 or 5x5 patches. So that because you're solving for constraints for matching the patches, because you're solving for little patches, that gives you more constraints. So then you can get out like the normal, and if the images have different lighting, you can solve for a lighting model for each image, and so it tends to work much better in practice than just 2-view stereo based on matching per pixel. Then there's like a lot of complexity, and where the complexity comes from is that you have to figure out which other images you're going to use to do your multi-view stereo. So you want other images that have that view the same points but also have a wide baseline. And you have to deal with things like that. Some parts of the scene might be occluded for some of those images, and that you might end up, and not all parts of the scene will be reconstructed. So it's common to use a region growing algorithm for this, where you start with, you assume that the sparse points that you reconstructed from OpenSFM or whatever are good, and they give you your initial estimate of the depth for the surrounding points, and then you grow out regions from those points. So MVE is a useful piece of software for this, and then this is a very valuable tutorial if you want to learn about this. It's 130 pages, and it's Yasu Furukawa actually graduated from here in like 2008. His thesis was on multi-view stereo. Now he's at University of Washington at St. Louis. But I think he wrote this while he was at Google. He was at Google for a while. So that's that. So this is just illustrating that you're trying to reconstruct this plane, the projection of a little 3D plane through a patch rather than a point through a pixel. So after you do multi-view stereo for your images, then you get a depth map for each image. And you can just pool all those points together. So since you know the camera poses, you can then, and the depth for all the pixels, then you can project that into like a 3D points, and then you just find the union of those points. And then you end up with this big, messy point cloud. Because there's noise, like something like this wall you'll get like a really fuzzy reconstruction where you've got points like that are plus or minus 1 centimeter off the wall. And so you want to try to solve for some clean surface through these points so that you can either create a mesh or just clean up your point cloud. So one of the best algorithm that I know of for doing this is called floating scale surface reconstruction. Poisson surface reconstruction is a classic algorithm, but this algorithm is better. The main idea of this and of many other surface reconstruction algorithms is that you create something called an implicit surface. So the basic idea of an implicit surface is illustrated here. So I've got this set of points. So here it's in 2D. And I want to try to, in this case, fit a curve through those points. So you represent, instead of representing the points, you represent a 2D map. Or in 3D, it will be a 3D volume. And what you're representing is, for each of these pixels, is it behind a point that I observed, or is it in front of a point that I observed? So like for this point here, I create some like area behind it where I say this area is behind the point, and so it gets, say, a negative value. This area is in front of the point, so it gets a positive value. And I do that for all the points, summing up whether like each pixel was behind other points or in front of it. And then I find the zero crossing. So I find the contour that has a value of 0 through that 2D map. So it's the same idea in 3D. So in 3D, for efficiency's sake, you compute, create an octree, which is a representation where you have big blocks in areas where you don't have a lot of points, and then you have little blocks in areas where you've got lots of points, so that you have an efficient representation of large spaces. You fill up this octree with your points, and then you compute this implicit surface function over the smaller cells of the octree. And the main idea of FSSR, floating scale surface reconstruction, is to use the normal and the scale of surrounding points to do a better job of creating your implicit surface function, so that in areas where you have a lot of detail, you get a sharp surface, and in areas where you don't have a lot of points, you get a smoother, large surface. So SFM has existed for quite a while, and it's been useful for quite a while, but it still has a lot of failure cases. So one of the main failure cases is where you don't have, where your images don't have enough overlap. So you take like some pictures over here, and then you take like a picture here, and then some pictures over here. And then if this picture doesn't have enough corresponding points with the ones that I took over here and over here, then I'll end up with 2 separate solutions. Another common problem is that you have featureless or reflecting surfaces, so like glass and water can be problems. They can actually cause outliers. Or just like blank walls, like in a corridor. You won't find matches, so you might not get a good solution. Images where you have pure rotation can cause problems because structure for motion, many parts of the process, you're assuming that you have images from different positions. But if you have pure rotation, then, and you try to solve for a relative position of those cameras, you could get something that's like seriously wrong. Even if you have small translation and it's mostly rotation, you might end up with a very poor estimate of the relative positions. And it's actually possible, even if that only happens a few times, it can destroy your solution. So you need to make sure to check for that. One of the worst cases is if somebody like takes basically a panorama, if they take a bunch of pictures like this and then go to another location and take a bunch of pictures like that, then it becomes really hard to do the 3D reconstruction. Where if somebody just walks around and takes pictures, then it's much better, ensuring that you have a good baseline between all of your images. And then the other major pain point is repeated structures like buildings and bridges, where locally points can look like they match really well, but they might be on like different sides of the building or different sides of the bridge or different parts of it. And then you end up with these outlying matches where you've got a lot of matches that kind of agree with each other, but they're wrong. And you end up like reconstructing the same wall in different places or creating other kinds of weird reconstructions. So any questions about incremental structure from motion? Yes?
So for the case that you just mentioned, where there's repeated structure, are there any good methods to handle that?
Yeah, Noah Snavely and Kyle Wilson have a paper on disambiguating structure from motion that I haven't tested yet, but it seems like a reasonable idea. So they use the match graph and do like a community, they compute the, I forget, some kind of correlation coefficient to see if like matches between 2 images are consistent with the graph as a whole, or whether it's kind of like, you can imagine if you have like these 2 clusters of images and then this image matches somebody over there, then you might be suspicious of that because it doesn't because none of its neighbors match this image over there. So you can use that to try to find matches that are unlikely. And then you can throw out those bad matches and then use some other processing to try to improve the stability of your solution. So that's one example. But there are some different methods that try to handle it, but it's still an open problem, I would say, as a whole. I'm just going to show a couple examples from from reconstruct. So, let's see. Right, so I don't know, I actually don't know where this one came from, but it's kind of cool. So here's an example of a reconstruction. So this was done with OpenSF, or, well, something that involves OpenSFM and MVE. And it's, so it's a whole city block. I don't have my mouse, so it's a little hard to control. But I can see, so here I'm showing all the cameras. So these little patches, so all these little patches, you can sort of see them in a grid as I move, there they are the cameras. And this is a reconstructed block. And then, so all these cameras have known pose, so then you have the images are aligned with the point cloud. So I'll show you another example that's where it's like a difficult case. So this is a railroad bridge. Oh, man. Let me see if I can zoom in without a mouse. All right, just a second. I might not be able to show this. Moving really slowly. All right, I have a way to do it. Oops. Okay, do it. Okay, so yeah, so here's another example. As you can see, there's a lot of trees, and I don't know if that's, I guess, snow or something. So the trees are not reconstructed with like a lot of precision, as you might expect. You just kind of get like blobby points around the tree branches. And actually the bridge, so things like thin structures are also difficult because like on the edges of structures, multi-view stereo will have problems because the patches will fall on and off the structure. And then like metallic surfaces can be kind of difficult. And then just like snow, I mean, there's a lot of challenges to this kind of data set. This is just to give you some idea of the kinds of reconstructions that are possible. If I had my mouse, I could move around a little bit more easily. But yeah, then I don't think I have any examples on here that I know that I can find easily. But there's also a lot of cases where it fails miserably, where we get like 20 solutions, or we get like one bridge sticking vertically out of another bridge, or you get like repeated structures. So it's definitely still a lot of stuff to do there. Right, looking for my mouse. Okay, so then, so the other method I'm going to tell you about is called affine structure from motion, or structure from motion under orthographic projection. And it's kind of a cute idea. So the idea, now you have a different model for your camera. So instead of, you're assuming basically that you're far away from the object, so that you can kind of think of it as like depth isn't going to affect its appearance. And then we have tracks or some correspondences of the points again, and then we're going to reconstruct the values from that. So this kind of assumption can work when the depth of the points in the scene is much smaller than the distances to the cameras. And also the cameras are not moving towards the scene or away from it, or at least their motion towards it or away from it is really small compared to the lateral motion. So the orthographic projection assumes that the position that a point projects onto the image plane does not depend on the depth. So I am projecting onto my u and v pixel position from x, y, and z. If I assume that my rotation is identity and no translation, then it's just u equals x, v equals y. Or I might have scaled orthographic where I have some scale times u and v equals x and y. So if I then have a rotation matrix, so now my image plane is rotated with respect to the world, then I have to rotate my scene point into the camera's view with some r prime f, and there's also some camera translation. So now this becomes the projection shown over here. So now my rotation matrix is just multiplying out these things by my 1, 0, 0, 0, 1, 0 matrix for the orthographic projection. My rotation matrix just becomes the top 2 rows of the rotation matrix. So this is a 3 by 3. So this becomes a 2 by 3 matrix, or it's basically a affine projection. So that's why it's called affine structure for motion. So this is a 2 by 3 matrix, and then times some 3D point plus a translation. So affine projection is a linear mapping in inhomogeneous coordinates from 3D points onto a 2D point plus some translation. And that translation is, the meaning of it is that it's the projection of the world origin onto the point. So if x is 0, then t, yeah, so at the world origin where x is 0, you'll observe you'll observe the center of the world at t. So now the problem is that we're given corresponding points, little x, in several frames, and we want to estimate both the 3D points, big X, and the affine parameters a of each camera. So the first step is just to get rid of that t, and there's a simple trick for doing that. So the trick is that you just normalize all your points by subtracting the mean value within each image. And then this shows why it works. So if you just do the math, if instead of representing the original 2D points, I represent the points minus their mean, where here I'm summing over all the observations within a given image, then if I substitute in the projection here for these points that I'm computing the mean for, then my sum over ti, since there's no subscript k, divided by n, will just be ti. So I get minus ti plus ti, so the ti's cancel out. And then I have a times some original 3D point minus an average of the original 3D points is equal to my a times the average, the normalized 3D points. So now all I'm doing by subtracting off the mean, by subtracting the means of all my 2D points that I see in each image, I'm solving for affine structure for motion where the cameras are now all centered around the world origin. So now I have 2D normalized points. So for each image, I subtract the average u and average x value from the points in that image. And I need to solve, I want to try to solve for the affine mapping and the normalized 3D point. So let's say if I knew the 3D points and I knew the affine parameters, so if I knew A and I knew X, where A is a 2m by 3 matrix, since I have m cameras and n points, so this is 2m by n and this is 3 by n, then I could easily compute the 2D points, right? So if I know the camera poses and I know the 3D points, it's easy to compute the 2D points. But unfortunately, we're trying to go the other way around, right? We have the 2D points, this big matrix of values. So I'm organizing my data by storing for every row I have, or pair of rows, I have the U and V values that are seen by a given camera. And for every column, I have a different observed point. So this column would be all the points that are, or a single point that's observed by all the cameras. And this row, or the top two rows, are the U and V values of the, or normalized U and V values of all the points that are seen by that camera. And I want to somehow take this matrix and extract the affine matrix for each camera and the 3D point for each observed point. So it's kind of looks under-constrained, right? So there's a bunch of constraints that we can use to actually solve this problem. So the first one is the rank. So what is the rank of this matrix of 2D points? So there's a... So what is the rank of this matrix, which is 2m by 3? What is the maximum rank it could be? 3, right? Somebody said 3. So if you have a k by n matrix, then the maximum rank of that matrix is the minimum of k and n. Also, if you multiply two matrices together, then the maximum rank of their product will be the minimum of the ranks of these matrices. So this has a rank of 3 at most. This at most has a rank of 3. And this also, this 2D matrix, this big matrix here, also has a rank of at most 3. So that gives us kind of our first clue. So now I can use... So now I want to decompose my 2m by n measurement matrix. So this is all the observed points arranged in this way where the columns correspond to points and rows correspond to cameras. And I want to factor it into this motion matrix, which is a 2m by 3 matrix of all the affine parameters, and my shape matrix, which is a n by 3 matrix of all the 3D point values. So I can get a factorization anyway using singular value decomposition. So when I do SVD on my measurement matrix D, I'll decompose it into some U, which will be 2m by n, a W, which will be n by n, and then V transpose, which will also be n by n. But I know that this W is only rank 3. So I can just force all the singular values except for the top 3 over here to be 0. And then correspondingly select only the first 3 columns of U3 and the first 3 rows of V transpose. So now I've got something that at least has the right shape. I've got my U, some kind of scaling 3 by 3 matrix, and V, where U3 is the shape that I want for my affine parameters, and V transpose is the shape that I want for my measurement, or for my points. So now I've got this factorization, and so I can create some initial estimate of my affine matrix and my 3D points just by pre-multiplying or post-multiplying this matrix by W square rooted W. It's just a diagonal matrix. So the square root is just the square root of the elements. The elements will all be positive. And then pre-multiply V transpose by W to the 1/2, right? So that gives me some initial estimate of an affine and motion matrix. I mean, my structure, which is the affine matrix, and my motion, which is the 3D point matrix. But there's an ambiguity here. So the ambiguity is that the decomposition isn't unique. So I could get the same matrix D if I post-multiply my A tilde by NEC and then pre-multiply X by NEC inverse, right? So if I substitute AC for A and C inverse X for X, then it will still equal D. But then my A and my X would be different. So we need to resolve that ambiguity. In order to resolve that ambiguity, we need some additional constraints. So, so the constraints that we have now are that these, so far, we haven't enforced any kinds of constraints on these affine matrices. So remember, this is a 2m by 3 matrix. So I can break it up into my 2 by 3 little camera matrices. And each row is basically saying what the axis is of that camera. So if I take the top row of A1, that's saying how a 3D point should project onto my U axis. And the second row of A1 is saying how a 3D point should project onto my V axis. But so far, these are unconstrained. And we know that U and V should be orthogonal, so that's a simple constraint. And for simplicity, we can also just say that and they have this, well, not for simplicity, they're orthogonal and they also have the same scale. So my pixels are square. So what that means is that the two rows of each camera matrix should be perpendicular to each other, and they should have unit length. So that gives us a set of constraints that we can use. That for each, the two rows of the affine matrix should have a dot product of 0, and they should each have a unit length. And so then I can solve for this C such that I want to solve for an affine matrix that's parameterized by C, where A1 transpose, or this AI1 and AI2, so this AI1 and AI2 are the two rows of the ith camera matrix. So I want each row to be unit length after given some C, and I also want them to be perpendicular. So that gives me 3 equations, and I have actually, it gives me 3 equations for every camera. And I've got a whole bunch of cameras. So I have 3 times m equations. And I'm trying to solve for some 3 by 3 matrix. So as long as I have at least a few cameras, I can solve for this. So the way you solve for it is you first solve for L. You say L is equal to C transpose. And then you can recover C from L using Kleski decomposition. Then you update your A and your X matrices by post-multiplying A tilde by C and pre-multiplying X tilde by C inverse. So to summarize this algorithm, you're given a set of m images and n tracked features. And this is the one that you'll be implementing based on your track points in homework 2. So you're given m images and n tracked features. We'll assume for now that you just see every point in every image. For each image I, you center the feature coordinates. So you subtract the mean U and V value within each image. Then you construct your 2m by n measurement matrix. That's just putting all your values into a big matrix together of this format. And so the J column contains the projection of point J in all views. And row I contains one of the coordinates of all the projections that are seen by a single view, the ith image. Then you factorize this matrix D by doing SVD and taking the first 3 columns of U and the first 3 rows of V transpose, or equivalently the first 3 columns of V. And then create W3 by taking the upper left 3 by 3 block of W. So you're basically saying that all the singular values after the first 3 are 0. Then you create the motion or affine matrix and shape 3D matrix by post-multiplying U3 and V3 by the square root of W. So that gives us our A tilde and X tilde, and then we eliminate the affine ambiguity using the equations that were shown in the previous slide. So solving a least squares problem. So this is, I've written it down as equality, but you're going to end up being over-constrained because you have 3 equations for every camera. So you have a whole set of constraints, and then you want to try to solve for the L that minimizes that in a least squares sense. So, so if you have, in practice, you'll often have tracks that are observed by only part of the sequence. And so you can deal with that in a way that's similar to the incremental perspective structure for motion. So you could just say, here, if these are the cameras and these are the points, you first solve for like the biggest block. So say you solve for like some block here where all the cameras observe these points. Then you can add other cameras based on those reconstructed points and then extend your points. And then slowly you grow out your solution, adding new cameras and adding new points until you solve for everything. So when you're done, it should look something like this. Or if you rotate it, if your solution is good, then when you rotate the 3D points that you reconstruct, the sides of the dollhouse should be perpendicular to each other. So I always thought that this dollhouse was just was like an actual dollhouse that somebody took normal pictures of, and affine structure from motion was an approximation. But I found out when I tried to do perspective structure from motion on it that it's actually purely affine. So it's a graphic. I think it's a graphically generated scene. And so it turns out that the fundamental matrix that you get is always degenerate because there is no perspective. So the plus is that you know that you can get a clean solution for it in your homework. So there's a nice explanation of affine structure from motion here, and also another good explanation of epipolar geometry and projective SFM there. So just to recap, like the whole dollhouse thing, which takes us from where we've got a set of images, we're detecting points and tracking them and doing structure from motion. So in the dollhouse sequence, you first detect points, for example, using Harris corner detectors. Then you use Lucas-Canati tracking to track the points. So now for the tracks are a set of observations where you're viewing the same 3D point in each image. So that's homework 2. Then in homework 3, problem 4, you do affine structure from motion from these tracked interest points. So you put everything into the measurement matrix, do your decomposition, solve for the orthographic constraints, and then you're done. So just a couple of tips for homework 3. So for the vanishing point problem, it can be helpful to estimate a lot of lines, use a lot of lines to estimate the vanishing points so that you get a more stable estimate. There's a post on Piazza about this, but the single view geometry chapter explains how to do that. It's good to not take the mean. Like, a tempting thing is to take, if you use a lot of lines, to find all the pairs of intersecting points, then take the mean. But that often gives you a really unstable estimate. It's often not great. It'll depend most on it'll be very skewed towards the lines that ended up being most parallel. For getting the intrinsic camera matrix, you can use a numerical solver like fsolve if you want. And for epipolar geometry, one thing is to make sure that when you compute the distance of a point to a line, so we have a constraint that x prime transpose fx equals 0, but x prime transpose fx is not equal to the reprojection error. So you have to compute to solve for it, you have to do fx to get your line equation. Then you have to normalize this so that a and b have a norm of 1. So you divide by the square root of a squared plus b squared. And now the distance of a point to this line will be the dot product of uv1 with abc. So this is the distance of some point x prime to this line. If you just look at the x prime transpose fx, then it'll be misleading, and you'll not be able to correctly find inliers. So there's a bunch, if you're interested in these topics, here's a bunch more readings. Some of them I already linked to, some are different links, but these are all classic SFM papers. And so that concludes structure from motion. So in the next class, I'm going to talk about clustering and using clustered interest points, and then using that to be able to quickly match images in large databases. Thanks.